All right, so it should be recording now. I can see the microphone moving in front of me. Let me go ahead and share the screen real quick. And let me know if you guys are able to see the screen there. All right, awesome, you can? Okay, cool. So, first thing, before I kind of start the session, obviously just want to make sure that I reiterate that for the people who are watching online, but I'm going to have exam review sessions Tuesday, November 29th from 1 p.m. to 4 p.m. That's weeks 10 and 11 review. Wednesday, November 30th from 1 p.m. to 4 p.m. weeks 12 and 13 review. Friday, December 2nd from 12 p.m. to 3 p.m. weeks 14 and 15 review. And then finally, the day of the exam, December 7th from 10 a.m. to 6 p.m. review, big review for the exam, the day of. So those are the designated review sessions that we have at the moment. But yeah, and those should be in the fishbowl room, hopefully. We got that reserved very early on, so we don't have to squeeze ourselves into that room at the MSLC again. But yeah, now without further ado, I think we can go ahead and get started now on the homework. So for this first problem, we have an IV bag, right? We have a 3 centimeter long needle at the bottom of a tube connected to an IV bag. It's used to inject a 125 milliliters of saline solution located H equals 70 centimeters above the needle over a 1 hour period. The viscosity of the saline solution is 1.1 millipascals per second, or 1.1 millipascals seconds, not per second, just seconds. And its density is 970 kilograms per meter cubed. You may assume the resistance to flow and fluid speed in the bag and the tube is negligible. Only the resistance across the needle needs to be taken into account. All right, so we can kind of ignore the resistance to flow and fluid speed in the bag and the tube. And then only the resistance across the needle needs to be taken into account. Right, so we're not worried about the resistance to flow and fluid speed in the bag or in the tube here just at this point. Right, so part A now is asking us if the veins gauge pressure is 5 millimeters of mercury, what will be the difference in the input and the output pressures across the needle in both millimeters of mercury and pascals? So when we're talking about difference in input and output pressures, right, that would indicate some kind of difference in pressure that we're looking at, right? Delta P, right? Difference in pressure. Now, if they're telling you that the veins gauge pressure is 5 millimeters of mercury, well, that's a pressure value right there. We don't necessarily have to convert things to absolute pressure. We can actually just go ahead and use gauge pressure if we wanted to. We just got to make sure that the rest of the parts, like if we have a second pressure point, then it also has to be in terms of gauge pressure and not absolute pressure, just to make sure that you get the right values and stuff. But anybody have any ideas as to how we can figure out the difference in pressure across the needle? Yep, exactly. Exactly, yep, that's the hydrostatic pressure equation, and we're absolutely going to use that. So for the hydrostatic pressure equation, right, we have PA, pressure at point A, plus rho GHA is equal to pressure at B, right, plus gravity R to begin with, rho GHB, right? So, first of all, right, if we want to figure out the pressure difference across the needle, right, we're looking at the pressure difference between like this point here and this point there, right? That difference in pressure due to the difference in height, basically. Can you guys not see my writing? Oh, shoot. Okay. It looks like it's going to be one of those nights. All right, how about now? Now you can. Okay. Awesome. So pressure at A, we can say, like I said, I usually like to say pressure at A is at the top, B as in bottom, right? So we can make this pressure point here, PB at the bottom, right? 70 centimeters? Yeah, 70 centimeters below the tube here, or below the IV bag here. So this whole height here is 70 centimeters. That's our height. So that being said, they told us that the pressure at B, or the pressure at the vein, right, the gauge pressure is 5 millimeters of mercury. Okay, well, excellent. 5 millimeters of mercury, that's our gauge pressure there. Okay, cool. How about at A? What would our gauge pressure be here? 0, exactly, right? So the gauge pressure at the top would be 0, because if we think about it once again, gauge pressure is just your absolute pressure minus your atmospheric, right? So we know that at the top here, they clearly tell us that it's atmospheric pressure, right? So if we were to say then the absolute pressure is, okay, that's 10 to the 5th pascals, that's atmospheric pressure, and then we subtract atmospheric pressure again, then we get gauge pressure is 0 pascals, or 0 atmospheres, or 0 millimeters of mercury, or whatever, right? 0 is our gauge pressure there. Because if you're at atmospheric pressure and you subtract atmospheric pressure, you should get 0 for your gauge pressure at the top at point A. Now, this becomes a 0, right? We have a specific height, and that's just due to that 70 centimeter difference there. And we have gravity and we have density. Now, the idea here is that you have to make sure that everything is in the proper values and units, right? So if we're going to have gauge pressure here, we're going to have gauge pressure there. So we're going to have that 5 millimeters of mercury on the right-hand side here. However, right, as we're accustomed to in this equation, we have values like kilograms per meter cubed for our density. We have meters per second squared for our gravity. Our height is usually going to be in meters, right? Now, with those values in consideration, that means that generally for the hydrostatic pressure equation, and not even generally, like this is going to be pretty much always, you are going to have your units be in pascals. That's just the preferred method, how you do things, unless you change around these values. But these values, right, are always, damn near always going to be kilograms per meter cubed, meters per second squared, and meters. So if you keep these the same, if these are our standard values in meters, in seconds, and stuff like that, and kilograms, all your SI units, then your pressure values have to be in SI units as well. And so for SI units, we use pascals, right? Now, that means we're going to have to convert from 5 millimeters of mercury to pascals, right? That's first. So we can say that, all right, write it over here, 5 millimeters of mercury. There are 760 millimeters of mercury in 1 atmosphere. And then in 1 atmosphere, right, there are 10 to the 5th pascals. And so that way we can get an answer of 657.9 pascals as our pressure reading at the vein here. So for PB, yeah, go ahead, Matthew. Yeah, like 101.3, you can do that as well. You can do that as well. The only thing that I would say is that I feel like this gives you a slightly more accurate answer, in my opinion. You can do the 101.3 Pascal like conversion rate as well. That's totally fine. It'll count for points just the same. You won't get any points off whatsoever. It's just that this is the method that I kind of prefer. It is a little bit longer in a sense that like you will go ahead and go from millimeters of mercury to atmospheres, from atmospheres to pascals. But the thing is, I feel like it gives you a much more accurate answer as opposed to 101.3. But either way is perfectly fine. I think, let me see here. Let me see if I can calculate that. So if you're saying like, what, 1 millimeter of mercury is what, 133.3 pascals? Yeah, I guess if you can multiply that as 666. Yeah, seeing like that answer is is quite a bit off in a sense. The work is exactly the same. It's absolutely valid. I just feel like, well, honestly, like you're not even quite sure like which one is accurate. I just feel like these are values that I have never seen changed. Like 760 millimeters of mercury is definite in a sense that that's everywhere. 10 to the fifth pascals, 1 atmosphere, that's everywhere. Though 101.3, like or 133 or whatever, right? However you choose to convert things, I feel like is a little bit more of an estimation, but I just prefer this method here just because I feel like it's a little bit more accurate. But does that sound good, Matthew? Okay, cool. All right, so that being said, we have our pressure value here in pascals, 657.9 pascals. And then this 0 here is also in pascals, because remember we did 10 to the fifth pascals minus 10 to the fifth pascals, and we got 0 pascals as our gauge pressure. So now we can start plug in the other values. So we have density is 1,000 kilograms per meter cubed. I'll forego writing the units for now just to save some space. But it's 1,000 kilograms per meter cubed times 10 meters per second squared times our height of 0.70 meters, right, which is 70 centimeters. 70 centimeters is 0.7 meters. That'll be the height at pressure point A here at the top, atmosphere, right? Oh, well, awesome. Thank you. I did not notice that. There we go. My bad. For those who are watching, I apologize. It's not 1,000. That 1,000's for water. I forgot that they have the saline solution here has a density of 970 kilograms per meter cubed. So thank you for catching that. I'm also frozen. No worries. All right, let me go ahead and share that again. All right, hopefully you guys can see that. All right, so on the other hand, we also have this term right here. And if you think about it, well, if we're at this bottom height and we're calling this our reference height at the bottom, and we're measuring from it to the top of the IV bag, then this height is actually 0. So this whole term goes to 0. So effectively, you don't even have to add anything here at the end, right? So that just leaves us with PB is equal to, or this PB here, the 657.9, right, is going to be equal to, wait, hold up. I did something weird here. Hold up. Mm-hmm. My bad. I see what I did. All right. We're off to a great start. So this 5 millimeters of mercury, so it is not the pressure that we use here at the bottom here. My bad. So, however, it is the final pressure, right? When you're figuring out your change in pressure. So our change in pressure is going to be equal to PF minus PI, right? We're trying to figure out what the initial pressure is, right? And that initial pressure is going to be that PB. And so from that PB, right, where I have now PI, we can take PF minus PI, or that PB essentially, and then figure out the change in pressure that we want. So once again, this goes to 0 because you're at a reference height of 0, and we're measuring from it to the top. Am I frozen again? Okay. Okay, so what do I want to say here? Yeah, so once again, we're trying to figure out the change in pressure, right? And we have this as our initial pressure that we want to figure out, right? This 5 millimeters of mercury, the 657.9 pascals, is our final pressure. right? So delta P is equal to PF minus PI. This PI is going to be the PB that we're looking for here at the vein. So when we figure out PB, we should get an answer of 6,790 pascals for PB, right? And then if we go back to our delta P equation to figure out the change in pressure, or the difference in the input and the output pressures across the needle, then we can say that the final pressure was that 657.9 pascals minus your initial, and that was the 6,790 pascals here, right? And so we should get a change in pressure of negative 6,132.1 pascals. So there's a pressure drop of 6,132.1 pascals. And then from that, we can also convert to millimeters of mercury, right? So we can say negative 6,132.1 pascals. There are 10 to the 5th pascals in 1 atmosphere. And then in 1 atmosphere, 760 millimeters of mercury, right? So that gives us around negative 46.6 millimeters of mercury for that pressure difference there, for that pressure drop. Wait, say that again? Yeah, that'll be a valid way as well. Yep. But that is part A there. Not too bad, but sorry for that mistake there at the beginning. Otherwise, any questions about part A, or does everything kind of make sense so far? Okay, I will take that as a yes that everything makes sense for now. So that brings us to part B. What is the flow rate of the fluid in SI units, right? So flow rate, we remember that's our Q, right? It's a measure of volume over time. So they told us that you're injecting 125 milliliters of saline solution, right? Now, how long were you injecting that saline solution, right? So they said, where is it? 1 hour period, there we go. So we have a 1 hour period, that's our time, right? And 1 hour, well, we never usually have anything in hours for SI units. We want to keep it in seconds. So 1 hour, right? I can do the conversion actually. You obviously have 60 minutes, right? And in 60 minutes, or my bad, in 1 minute there's 60 seconds. So if you just multiply by 60, you're gonna get 1 hour is also equal to 3,600 seconds, right? And so for our volume now, we have that 125 milliliters. We'll convert that to liters so we can have something in SI units here where we have 0.125 liters per, or not per, but divided by 3,600 seconds, right? Then we have something in liters per second. Now, for the flow rate, our SI unit should be in meters cubed per second. So we have to convert now the liters to meters cubed. So once you do this 0.125 divided by 3,600, you should get something around like 3.5 times 10 to the negative 5 liters per second. Or let me write it this way. Liters per second, right? So I want to keep the seconds the same, but now I know that I can use this conversion rate. 0.001 meter cubed is equal to 1 liter. And so that way, if I multiply by 0.001, I should be able to get 3.5 times 10 to the negative 8 meters cubed per second as my flow rate in SI units. Does that make sense so far? Okay, awesome. So that's our flow rate for B. Now for C, they're asking us about the radius of the needle. So we have a value like flow rate, right? We calculated before the pressure drop. How does the radius come into play at all? How are we supposed to figure out the radius of this needle from the flow rate and something like the pressure drop here? Any ideas as to how we can figure that out? Yeah, no, that's perfect. Yeah. Yep, exactly. So we're going to use this Poiseuille's equation, right? So delta P is equal to negative Q times R, where Q is your flow rate, R is your resistance. And like Anna said, the resistance here is 8 times viscosity times length divided by pi r to the 4th, right? So for our flow rate, we're just going to use the flow rate here in SI units that we figured out. And the resistance, well, we can calculate that out. And we have our pressure drop here from the beginning, which was the negative 6,132.1 pascals there. So this is negative 6,132.1 pascals, and then this negative Q here is negative 3.5 times 10 to the negative 8 meters cubed per second. And our, am I frozen? Okay, one sec. There we go. So we have our resistance here, that's 8 times viscosity. So our viscosity, remember, that was 1.1 millipascal seconds. And that's the same as 0.0011 Pascal seconds. So we have to make sure everything is in Pascal seconds, meters, seconds, stuff like that. You can convert from 1.1 millipascals to Pascal seconds just by kind of dividing by 1,000 there, right? So you have this 1.1 and you move it back 3 decimal points. So 1, 2, 3, and gives you 0.0011 Pascal seconds. And then times your length, right? The length there of the needle is 3 centimeters, right? Which is 0.03 meters. And then we can divide by pi times the radius to the 4th, right? And we're trying to figure out that radius anyway. So if you do your rearrangement, move things around, right? You should get your radius equal to this really big equation where you're taking the 4th root of 8 times 0.0011 Pascal seconds, right? Times 0.03 meters times negative 3.5 times 10 to the negative 8 meters cubed per second divided by negative 6,132.1 pascals times pi. That's all under the 4th root here. Alternatively, if you're not sure how to plug in the 4th root in your calculator, what you can do is just like take this whole thing and take it to the power of 1/4. That also works to give you your 4th root there. But you can see here that it's basically what I did is I multiplied the pi r to the 4th, or at least I multiplied over the r to the 4th to the left-hand side here. So you can get negative 6,132.1 times r to the 4th, and then you divide over negative 6,132.1. So that's why it's 8 times 0.0011 times 0.03 times negative 3.5 times 10 to the negative 8 divided by that pressure drop times pi. So essentially I just brought this over here and brought this over there, divided it over. That's why you can see this is the same, this is the same, this is the same, this is the same, 0.03, 0.03, negative 3.5, negative 3.5, right? And then we divided over the negative 6,132.1, and we're left with the pi there as well at the bottom. And we took the fourth root, right, on both sides of the equation to cancel that out. But yeah, in the end, for your radius value, you should get 1.48 times 10 to the negative 4 meters, right? That's going to be the result of this long equation here, and that's going to be in SI units. However, they want it to be in millimeters, right? So if we convert that to millimeters, we should get a radius of 0.148 millimeters, and we can do that just by doing, let's say 1.48 times 10 to the negative 4 meters, right? In 1 meter, it's 100 centimeters. In 1 centimeter, it's 10 millimeters, right? So you can do that conversion as well to get the answer for your radius in millimeters. Sound good for problem 1? Okay, all right, just want to make sure. Alrighty, so problem 2 now, atherosclerosis. I always found this funny. I think, I don't know, I had this conspiracy theory that the professors are a tad bit liberal, because this problem just started off with Donald's aorta is 8 centimeters long, and in the absence of any plaque buildup, has a diameter of 2 centimeters. The viscosity of blood is 10 millipascal seconds. So there's a lot of Donalds in the world, but there's only one that comes to mind if I think about his aorta being clogged up with plaque deposits. But yeah. So anyway, I will probably start calling on people, I think, because I think the tonight is a little bit less active than usual, so we'll see here. All right, now that we have all this information, right, that the aorta is 8 centimeters long, you can say that's our length, and then we have a diameter of 2 centimeters. The viscosity of blood is 10 millipascal seconds, right? I have all that information. Now it's asking us, or it's saying, right, the pressure drop across the artery with no plaque buildup is 20 pascals. What is the flow rate of blood through the artery? So let me see here. Yeah, excellent. Yep. So we have a volunteer. All right, excellent job, Carlos. Yep, we can use the same equation from part C in problem 1, which is Poiseuille's equation, right? Delta P is equal to negative QR, right? Or QR, my bad. Right, so, or it is, yeah, it is negative QR. I don't know why I put QR there, just QR. Yeah, negative QR. So it's frozen. All right, 1 second. Let me reshare it real quick. So Is it pressure drop across the artery with no plaque buildup is 20 pascals? What is the flow rate, right? So we're trying to figure out the flow rate here, Q. So this pressure drop, right? Common mistake people might make is they might just plug in 20 and then just leave this negative sign here, and then they get a negative answer for their flow rate, right? Which doesn't make any sense. Now, the idea here is that when you say pressure drop, right, I dropped 20 pascals, and that's a difference of negative 20 pascals, right? And so your negatives will end up canceling out. So negatives cancel out with negatives, and that's why you can have a positive answer there for your flow rate. But this resistance value here is equal to 8 times viscosity times your length divided by pi r to the 4th, right? So we have this 20 Pascal times pi, right? Let me actually make this a little bit smaller here, move this over. So 20 pascals times pi times the radius, right? So we had a diameter of 2 centimeters. The radius is half of that diameter, right? So our radius is 1 centimeter, and 1 centimeter we can convert that to meters, which is 0.01 meters raised to the 4th power, and then divided by 8 times viscosity times length. So viscosity is 10 millipascals. We can divide by 1,000. We can get 0.01 Pascal seconds, and then multiplied by our length there, which was the 8 centimeters, which is 0.08 meters, right? So basically what we did is take the pi r to the 4th multiplied over here, and then divide over the 8 times viscosity times length, so we can isolate Q. And obviously these negatives canceled out. So once we do that, we should get a Q value here. Our flow rate should be 9.82 times 10 to the negative 5 meters cubed per second. So that's our flow rate there, 9.82 times 10 to the negative 5 meters cubed per second. Excellent. So moving on now to part B. As a result of plaque buildup, the radius of the artery is reduced to 25% of its original value. Now, what is the new flow through the artery with the constriction, assuming the same pressure drop as before the plaque clog, right? So we have to figure out this new flow rate with the constriction, assuming the same pressure drop. And yeah, to convert millipascal seconds, we only divide by 1,000. Exactly, yep. So essentially, it's going to be the same, right? Same Poiseuille's equation, negative QR. This delta P here is that's going to be that same negative 20 pascals. So the negatives will cancel out. And now we just have to figure out this new... Yeah, go ahead, Matthew. Yep, exactly. So if the radius is reduced to 25% of its original length, well, if we know that our original length of the radius was 0.01, right, we can multiply by 0.25 in order to get our new radius, right? And that gives us an answer of like 0.0025 meters in that case, right? So we can do is essentially just copy and paste this exact same deal here. This is our Q, except that now our radius is going to be 0.0025 meters, and that's raised to the 4th power, right? You have the same viscosity, you have the same length, same pressure drop, all of that, and then that should give you a new flow rate of 3.83 times 10 to the negative 7 meters per second for our new flow rate. Now with part C, what would the new pressure drop across this section of artery need to be to bring the flow back up to the original level, right? So if we have this resistance like component here, right, the same resistance based on this new constriction, right, and we want to bring things up back to that original flow rate that was unconstricted, right, then what would the new pressure drop have to be? Once again, this is going to be the same Poiseuille's equation, right? We just now need to figure out what the new pressure drop would have to be to maintain this 9.82 times 10 to the negative 5 meters cubed per second flow rate with this new constriction resistance value, right? So our QR here, our Q is going to be that, what is it again, 9.82 times 10 to the negative 5 meters cubed per second, right? And then our resistance value here should be that 8 times 0.001, or not 0.001, 0.01 Pascal seconds. That's our viscosity, times the length, which was 0.08 meters, right? Divided by pi times r to the fourth. And our radius, remember, because if it's constricted, it's now that new 25% of the original value. So it's 0.0025 meters there, raised to the fourth power. And that should give us our new pressure drop, right? In that case, with this pressure drop, we can see that it's going to be negative 5,121.3 pascals for our pressure drop, right? That'd be the new pressure drop to maintain the original flow with the constriction. So the blood pressure would have to drop to maintain the same amount of blood flow given that new constriction there because of the plaque buildup, right? Finally, part D is assume that Donald has had the plaque buildup given above, with all other blood vessels remaining unchanged. Originally, Donald's blood pressure was 110 millimeters of mercury, but it increased to keep the flow through the artery at its pre-clog rate. Compute Donald's new blood pressure and determine what level of hypertension he's at. So pre-hypertension is above 120 millimeters of mercury. Hypertension stage 1 is above 140. Stage 2 is 160 plus, and 180 plus is hypertensive crisis. So they also gave us a hint here. They're saying before the plaque buildup, this piece of artery contributed 20 pascals to the measured blood pressure. With the plaque buildup, it contributes 39 millimeters of mercury. So basically, trying to figure out this new blood pressure, determine what level of hypertension he's at. So we had the blood pressure drop, right, that we see here, that negative 5,121.3 pascals. That's our pressure drop that we see, right? There's a final pressure and an initial pressure, right? What they're asking you now, right, they told you that the original pressure is 110 millimeters of mercury, right? And then it says it increased to keep the flow through the artery at its pre-clog rate. So this is a little weird because the way I'm reading it now is like, I guess there wouldn't be a negative sign. But yeah. Mm-hmm. Yeah. Yeah, I'm not sure here because like it says, yeah, I guess. Oh, well, I guess they want you to just look at the blood pressure increasing in this case instead of decreasing to keep the flow through the artery at its pre-clog rate. Yeah, I guess that makes sense. That should make sense. Mm-hmm. Mm-hmm. Yeah, the negatives. Oh, okay. Actually, hold up. Yeah, the negatives. Yeah, should will end up canceling out, I guess. Yeah. Okay. Okay. Yeah. I guess we'll just have a positive value here for your pressure instead of a negative value there, just to show that the blood pressure increased here. Because if you're increasing blood pressure, right, then you wouldn't have a pressure drop in a sense. So it'd be the same value here, just positive instead of blood pressure drop, that it increased instead to keep the flow through the artery at its pre-clog rate. So we have this 5,121.3 Pascal pressure increase, right? And our initial was 110 millimeters of mercury. So in order to figure out the final, right, we can just convert this to millimeters of mercury, and we have this in millimeters of mercury, and then the final will be in millimeters of mercury as well. So actually, hold up. I take it back. We don't actually even have to convert because they already kind of gave us this anyway. It said with the plaque buildup, it contributes 39 millimeters of mercury as our pressure drop. If you end up doing it, like if we did 5,121.3 pascals, right? They just made it easier. Convert to millimeters of mercury. You should get like 38.9 millimeters of mercury. So they already gave us the pressure drop here in millimeters of mercury with the plaque buildup, because they said without it was 20 pascals, with it's 39. That's a lot easier than that on us. So 39 millimeters of mercury, PF minus PI, that was 110 millimeters of mercury. And if we add that, we should get a final pressure of 149 millimeters of mercury. So yeah, if you go ahead and calculate the conversion from 5,121.3 pascals to millimeters of mercury, you get 38.9. Same thing here, 39 around that value, right? They just gave us the value here in the hint, as opposed to us going ahead and calculating it out, which is a lot easier and very helpful. So yeah, this here, they were talking about pressure drop, so we had to make the values negative there, right? But here they're talking about a pressure increase, so your delta P would have to be positive to show that the pressure increased. I always have difficulty to kind of like visualize pressure increase, decrease stuff, especially when it comes to blood. Like when it comes to any other fluid, it's fine, but because blood is a little bit different, a little bit different than water, and how blood pressure kind of works in the body, things are not exactly ideal. And so I feel like things are a little bit backwards when it comes to blood, and so it's very difficult for me, I guess, to kind of interpret some of this stuff sometimes, because I feel like if we're going by continuity equation, Q1 equals Q2, right? If your area decreased, like things got more constricted, then you expect velocity to go increase, right? To maintain the same flow. And we know by the Venturi effect, or by like, if we use like Bernoulli's equation, if that velocity increased through that, like remember we had those like little, like basically had like this idea here where you had like this big area and then this smaller area here, and that through that smaller area you have an increase of velocity but decreased pressure, right? So there should be a pressure drop. So I guess, like, I don't know if that's just like a decrease in absolute pressure in that case, and then there's increase in blood pressure, like the arteries would constrict. But that doesn't make any sense because, well, like, I don't know. I'll leave this to like when I look at the cardiovascular chapter in the MCAT. But for now, like, oh shoot, yeah, what level of hypertension? Well, if he's 149, right, then what is it? Yeah, hypertension stage 1. Yep. So since he's at a final pressure above 140 millimeters of mercury, it should be hypertension stage 1. Sound good for this problem here? All right. take that as a yes for now. Problem 3 now is fluid films. This is where we get into like adhesion, cohesion, and surface tension. So, problem 3, you're investigating the properties of an unknown fluid. You create a flat film using the apparatus to the right, which has a rigid U-shaped frame and a light movable pin. The frame is oriented vertically, as shown in the figure. And you find that if the pin has a mass of 30 milligrams and a length of 2 centimeters, that it experiences an upward acceleration of 26.8 meters per second squared. So for part A, they're asking us, what is the cohesive surface tension of the fluid? And that'll probably help to draw a free body diagram for the pin first. So let's begin drawing a free body diagram first, right? So what forces you guys think are going to be acting here for the pin? Yep, excellent. We should have a tension force, 2 tension forces exactly, and gravity. So gravity is pulling us downwards, and then like 2 tension forces pulling back upwards like that. Excellent. And frozen? Okay, 1 sec. Yep, 2 tension forces and a gravity force pointing downwards like that, right? So, to figure out cohesive surface tension, right? And we have this free body diagram, an indication of acceleration, a mass value, stuff like that, right? Well, we can start writing out a F net equation, right? So we have F net is equal to mass of that pin, right, times the acceleration of the pin, and that's equal to 2 of those Ft forces, the tension forces, minus mg, or minus the force of gravity, right? And then, what was I going to say? We can rewrite the forces of tension here, right, with the surface tension kind of equation here. So we can write 2Ft as 2 times the surface tension times the length, right? Because, what was I going to say? The surface tension is not equal to the force of tension there times the length, or divided by the length, right? So if that force of tension, if we isolate for the variable, force of tension should equal that surface tension times length. And so we have 2 of these, so it would be like 2 times the surface tension times the length for our 2 FTs here, right? And that's equal, or that's minus mg there, right? So now we're just essentially just solving for our surface tension. And we have this mass value, we have the acceleration, so we can kind of isolate for surface tension and solve for that, right? So we can see here that MA pin plus mg divided by 2L should give us the surface tension, right? So if we just add this over here and divide by 2L, we should get the surface tension alone, and then we can calculate for that, right? So the mass of the pin, that was 30 milligrams, right? Fancy Y. This is gamma, I believe, right? Yeah. So, density, fancy P. Surface tension is fancy Y. Let's just keep it that so people can remember it. I think I had a lot of students like, I think one student like went up to the professor and was like, yeah, fancy P. And he was like, what the hell is fancy P? And so like I had like a partial negative influence on the students with regards to like these Greek letters. But yeah. So yeah, let's just call this fancy Y and density is fancy P, just for the sake of you guys can like remember it. And it's a funny way to kind of remember it too. So no harm, no foul. But anyway, for our mass of the what's it called? The mass of the pin, 30 milligrams, right? So that's 3 times 10 to the negative 5 kilograms. Yeah, it's definitely a throwback to Gen Chem. Multiply by the acceleration that we had, 26.8 meters per second squared. And then we can add that to, let me actually move things a little bit to the left here so we can have more space. Plus that same mass, right? 3 times 10 to the negative 5 kilograms times gravity now, 10 meters per second squared, and then divided by 2 times the length, which that length was, what, 2 centimeters, which is 0.02 meters, right? And then that gives us a surface tension, fancy Y, of 0.028 newtons per meter. Fair enough for the surface tension here? But yeah, part B, saying a droplet of this fluid with radius 4.6 millimeters is dropped from a pipette at sea level. What would the gauge pressure inside the droplet be? So looking for gauge pressure inside, basically. So, all right, let me see who hasn't spoken up today. So Carlos, I think you helped with like 1 or 2 parts for one of the previous problems. Anna, you've been very helpful tonight as well. Matthew, I think you've spoken up, or at least like you've asked a question for like one of them. So that leaves the rest of you guys. Anybody want to volunteer, or should I ask, or should I just call on someone? You don't have to have like the whole problem figured out, by the way. I just want to make that clear. Like you can at least like let me know like what equation we could use as well. Like that's a very valid way to participate and shows that you're kind of engaged in thinking through this stuff. But not quite the hydrostatic pressure equation. Kind of similar to it, but I mean, I have no problem with that. I just want to make sure the rest of the students here, like as well, are like kind of participating and staying engaged. Because like if you guys don't understand, like it's totally fine. Like no worries at all. That it's not something you have to like be embarrassed about whatsoever. Like we're all here to kind of like learn. So I just want to make sure that like if you guys don't understand something, then we can kind of figure that out, right? Let me see here. So let me know if I'm mispronouncing it, but Imani, do you want to give it a shot? At least like let me know what equation you might be thinking of using. And please correct me on the pronunciation as well. Mm-hmm. Mm-hmm. Yeah, so let me help you kind of like walk you through it, right? So we have this pipette, right? So imagine like a pipette, or holding it up, right? And we're gonna drop a few drops of the liquid, right, or the fluid from the pipette. So let's say like this is the pipette here, and we're looking at it, right? Am I frozen? Okay, one sec. Let me kind of go ahead and reshare there. So basically what we're looking at here is kind of like if the fluid is essentially filled up all the way here, right, and we're dropping it here at the bottom, right? We can think about this is the fluid level here, and then anything down here will just fall through the pipette and into the water, right? So there's a pressure inside the liquid itself, right? Or the droplet itself, right? And then there's also pressure outside, right? That pressure outside is in contact with the air, right? So where we have this kind of idea of P in versus P out, right? There's a specific equation to use for this. I don't know if anybody, or this is triggering like your, yeah, go ahead. Yep, exactly. Excellent. Laplace's equation, right? I think it's Laplace's equation. I'm not sure if it's Laplace or Laplace, but I go Laplace. But yeah, excellent job. So it is Laplace's equation, right? And that's going to be P in is equal to P out plus 2 times your surface tension divided by your radius of curvature, right? So excellent job. That's the equation that we're looking at here. So hopefully that kind of triggered your memory. I think this is like what it looked like from one of the slides. Let me see if I can pull it up here. So I don't know if it's up here somewhere. Yeah, I think it is up here. So yeah, here we go. This is what I was kind of going for, where we have P in, P out, and then this is the equation to use. This is Laplace's equation, right? So this out here would be like the outer part of the pipette without any liquid that's going to be in contact with the atmosphere, and then the inside here would just be the inside of the fluid that you're trying to drop in, right? So what we're trying to figure out then is the gauge pressure inside the droplet, right? So P gauge in versus P out plus 2 times the surface tension divided by radius of curvature, right? Now, what do I want to say? Yeah. So usually this is written in terms of like absolute pressures, right? So if we wanted to figure out P gauge in, that's going to be the absolute pressure of the inside minus the atmospheric pressure, right? So this absolute pressure here on the inside minus the atmospheric pressure is essentially the same as P in minus P out, right? Because P out, the outer portion here, is the atmospheric pressure portion. So this is the part that's in contact with the air. This is the liquid here. This is the air here. Air, liquid on the inside there, right? So if we're trying to figure out the gauge pressure of the inside the droplet, that's the same as saying the absolute pressure of the inside minus atmospheric pressure. Well, if this is in terms of absolute pressures, right, then P in minus P out, where out is the atmospheric, just subtracting P in minus P out will give us the P gauge in, right? That would give us the gauge pressure there. Now, the way that's set up then, if this P in minus P atmosphere is also equal to P in minus P out, given that out is atmospheric pressure, then we can just say that this is equal to 2 times the surface tension divided by your radius of curvature, right? This will directly give you the gauge pressure on the inside. You can also simply just think about it as, okay, well, if I didn't want this to be in terms of in terms of absolute pressures, and this was gauge pressure and this was gauge pressure, well, the gauge pressure of atmospheric pressure is what? What would the gauge pressure of the atmospheric pressure be? Zero, exactly. So if this goes to 0, if P out is 0 in terms of gauge pressure, then we're just looking at P in, and then P in is 2 times the surface tension divided by radius of curvature, and that would just directly give us our answer in gauge pressure anyway, right? Same deal. But like I said, so then we just have, if we wanted to figure this out in terms of gauge pressure, which is a lot of a lot easier and a lot quicker, right? Then we can just say P out is 0 in terms of gauge pressure. And then we can have P in is equal to 2 times your surface tension divided by radius of curvature. Surface tension was what? 0.028 newtons per meter. Am I frozen? Okay, one sec. Okay, so 2 times surface tension, which is 0.028 newtons per meter, and divided by the radius of curvature, right? That was that 4.6 times 10 to the negative 3 meters there, which is the 4.6 millimeters, right? And then that gives us 12.2 newtons per meter squared, and that's the same as 12.2 pascals for our gauge pressure Pn there. Right? That would directly give us the gauge pressure. Alternatively, right, like I said earlier, if you wanted to have things in terms of absolute pressures, then what you would do is you do the Pn minus the P out. P out would be your atmospheric pressure, like 10 to the 5th pascals, right? And then you would actually not minus P out, but essentially you would just take 10 to the 5th, add this to the 2 times surface tension divided by radius of curvature, and then that's your absolute pressure. Convert that to gauge pressure. So what if you had like 10 to the 6th pascals is your absolute pressure from using this equation here for P in, then just subtract 10 to the 5th, and then that would give you your gauge pressure, right? But it's just much easier, I think, to have things, or to have everything in terms of gauge pressure from the beginning. So P in gauge, P out gauge. Out is atmospheric pressure. Gauge pressure of atmospheric pressure would just be 0. So then you can just find out the gauge pressure of the inside just by calculating 2 times the surface tension divided by the radius of curvature without adding 10 to the 5th and then converting to gauge pressure and all that business. So, yeah, if you get exactly 12, I think that's fine. I don't know if let me recalculate mine out here just to make sure. Yeah, I got like 12. I still got 12.2 something, 12.17, I think. But, yeah, if you get exactly 12, that might just differ based on like your surface tension from part A or something. Yeah, but that's fine. Part C now is saying the droplet falls on a horizontal sheet of plastic, making a contact angle of 125 degrees. What is the adhesive surface tension? So adhesive surface tension, this is just a straight up plug and chug for part C. So it just depends on whether or not you remember the adhesive surface tension equation. And you're more than welcome to like just use your equation sheet and shout it out or type it in the chat. And like I said, I prefer to hear from people that haven't spoken up yet, just I'm going to make sure that everyone's engaged. That's all. So if you haven't spoken up yet, this might be a prime time opportunity just to name out an equation and just get your participation for the night, I guess. Yep, so the second one is correct. The first one, right, if we just did the radius, right, that's the, what's that called? Like the cross-sectional radius, basically, divided by our radius of curvature, and then that's equal to cosine theta. Well, that doesn't really give us a way of figuring out adhesive surface tension, but the second equation is absolutely correct. And I can see someone else also pointed out in the chat. Our adhesive surface tension, that gamma A, well, that's a horrible, that looks more like torque, not gamma. There we go. So adhesive surface tension is equal to the surface tension there. Am I frozen again? Okay, one sec. Okay. There. So adhesive surface tension is equal to the surface tension there times 1 plus cosine theta. And in this case, theta is 125 degrees, right? And our surface tension here, we already have it, which is 0.028 newtons per meter. right? So simply, we can just figure that out, and we should get 0.0119 newtons per meter for our adhesive surface tension, right? That's the adhesive surface tension for part C. Pretty simple, plug and chug, not too bad, right? D, suppose you wanted to increase the contact angle. Could you do so by changing the type of plastic in the sheet, changing the adhesive surface tension? If so, should you increase or decrease adhesion? So if you wanted to increase the contact angle, could you do so by changing the type of plastic in the sheet, which would then change the adhesive surface tension? And if so, should you increase or decrease adhesion? Anybody have any ideas about this one? Yep, you could change, yep, exactly. You can change the plastic sheet. You can change the type of plastic or material that's used. And then how would we want to change the adhesive surface tension? Should we increase adhesive forces or decrease adhesive forces? So I see an increase, but I think it would be decrease because essentially if you change the material to reduce adhesion, right, then we increase the contact angle. So like, yeah, if you wanted to increase the contact angle, if you just kind of like, if you do a calculation, I think, let me see here. So I don't have a calculator on me, shoot. Actually, okay, hold up. Let me see if I can just use my phone calculator. Okay, there we go. There's that. And then, yeah, just want to make sure. There we go. So if you were to use your calculator, right, to kind of prove this, if you were to increase this contact angle, right, if you were to increase this contact angle, let's say from 125 to 140, right, and you multiply, and you add this to 1, and you multiply by your surface tension, right, you would get a smaller adhesive surface tension, right? So if I increase the contact angle, I'm going to decrease my adhesive surface tension. So I could change the type of plastic in the sheet, change the material to change the adhesive surface tension, and the way I would change it would be to decrease it, right? So if I increase contact angle, right, if I increase theta, I decrease my adhesive surface tension, right? And you can use the equation to kind of like show that as well if you wanted to. But yeah, you could change the type of plastic or material, and we would change the material in a way to reduce adhesion, because if we reduce adhesion, we would have to increase the contact angle, or vice versa. If we want to increase the contact angle, this would result in a decrease in surface, what I want to say, adhesive surface tension. That's what I meant. So yes, we can change the type of material. Actually, you know what? Because my handwriting is not going to be the greatest when I write a lot of stuff down. So let me just go ahead and type it up. I feel like that would be a lot better. So yes, we can change the material or plastic in the sheet, which would change the adhesive surface tension. To increase the contact angle, there must be a decrease in adhesive tension, right? Thus, we would change the material in a way to reduce adhesion, because if we reduce adhesion, we increase the contact angle. There. That's kind of the gist there. But now, finally, we're at problem 4 here, which is capillary action. So, what do I want to say? Like, this stuff is also based on like adhesion and cohesion. So, I think this problem is like very, very simple actually. Like I said, this problem I don't have like an answer key for or anything like that, so I'm just gonna hope for the best, honestly. Like I'm confident in what I'm doing, but yeah, I just don't have any way of checking exactly. But there is a different problem for this homework that I have as my problem 4, or at least problem 1 for me was different. Like problem 1 that you guys have here was my problem 3, I think. So problem 1, 2, and 3 are the exact same as what we had, just different in a different order. And then problem 4 was different for us. So we just have a different 4th problem. But I can post that, like I said, on the Google Drive, so you guys have access to that extra practice problem there for your own reference. But for problem 4, capillary action, when a very thin tube, a capillary, is placed in a container of oil, the combined effects of cohesion and adhesion cause the oil to rise up. These competing surface tensions also result in the meniscus, shape of the surface, to be curved, with a characteristic radius of a curvature RC. Now, oil has a density of 700 kilograms per meter cubed and surface tension of 40 millinewtons per meter. The cross-sectional radius of the capillary tube is 0.73 millimeters, and the contact angle of the oil surface of the meniscus with the glass walls is 50 degrees. That's a lot of information there. We know that the density, 700 kilograms per meter cubed, right? We have a surface tension of 40 millinewtons per meter, which we're bound to convert to SI units probably, right? A cross-sectional radius, so just a regular R, of 0.73 millimeters, right, which we're also bound to convert to SI units. And then our theta, our contact angle, is 50 degrees, right? So for part A, what is the radius of curvature of the meniscus? So I think someone, I can't remember who said it earlier, they'd mentioned an equation that we could use to kind of relate or figure out radius of curvature. So what do you guys think that's going to be? Yeah, so I see R divided by RC is equal to cosine of the contact angle, right? So R divided by radius of curvature should be equal to cosine of the contact angle, right? So R here is our cross-sectional radius. That would just be this radius here, not this one, but this one. And that's the 0.73 millimeters, right? So if we rearrange the equation, multiply over RC, divide over cosine, then we can see that 0.73 millimeters divided by cosine 50 would give us our radius of curvature. But we want things to be in SI units preferably, right? I mean, they really don't state that you have to have it in meters, but I feel like it might just be better, especially later on, to have it in meters if we're figuring out like gauge pressure and stuff here later on. So 0.73 millimeters, right? We're just going to divide by 1,000 to get it to meters. So 0.73 divided by 1,000, that should give us 0.00073 meters, right? And divided by cosine 50, and that would give us RC, right? So let me see here, because I don't have I have a calculator on me. I'm just going to use my phone calculator. Cosine 50. We got around 0.114 meters. Hold up, maybe I did something wrong here. Oh, I see, I forgot the zeros there. Maybe 1 second, let me just do that again. 0.64, okay, 0.000073 divided by 0.64. Yeah, 0.00114 meters for your radius of curvature. Right? And if we were to multiply that, that's in meters, right? And if we multiply that by 1,000, so move over 3 decimal points, we get 1.14 meters, millimeters roughly, so 1.14 millimeters as well. Now for part B, where they're asking about, yeah, you can keep it in meters. I think it's going to be more beneficial probably to keep it in meters. But yeah. So now, for part B, they're saying, what is the gauge pressure at the top of the column? Hint, use the Laplace equation, right? So we have Pn, right? Or essentially would be, Pn is basically our P top here, right? Pn is our like a P top. So P top is equal to P atmosphere, which is like our P out, right? Plus 2 times the surface tension, right? Divided by, I almost forgot what it was. RC, that's what it was. For some reason I'm thinking length, but yeah, it's radius of curvature. See, sometimes I even forget the equations. But when they're asking about gauge pressure, right? What is the gauge pressure at the top of the column? Well, what is the gauge pressure of atmospheric pressure, or the outside here? Zero, right? Yeah, so atmospheric pressure, the gauge pressure for it should just be 0. So then we're just left with P top, which is what we're trying to figure out. The gauge pressure for it would just be 2 times the surface tension, right? Surface tension was 40 millinewtons per meter. So if I want to convert that, I think we can just divide by 1,000 once again to get newtons per meter, right? So if we plug that in, right, and then divide it by a radius of curvature, that should give us our, what's it called? Pressure at the top, right? So our surface tension is going to be 0.04 newtons per meter in that case. And then divided by a radius of curvature, which is that 0.00114 meters. Oops, 114. And then that should give us our P top, right? So 2 times 0.04 divided by 0.000114. So I got like 70 newtons per meter squared, which is like 70 pascals, but I'm not sure if that's quite right or not. I don't know. Did you guys get like around 70 as well? Yeah, 70. I got 70.2, but I don't know. That feels a little bit weird, but yeah, I don't see anything that would be wrong with this. P top, P atmosphere. Yep, 2 times 0.04. Yeah, I guess, yeah, 70.17 is exactly what I got, Carlos. So, I mean, I'm hoping that's right. Yeah, 40 millinewtons is 0.04 newtons per meter. I just wanted to make sure that I got that conversion right. And then just divided by radius of curvature, which would be our 0.00114 meters. Mm-hmm. Oh, wait, hold up. But I mean, if like, so hold up. If I move back to the slides real quick, well, that's not it. There, I just want to move this. P in is equal to P out. Yeah. So, I mean, the way they have it set up here is the inside is equal to the outside plus this. So, I mean, so this is the P atmosphere basically, right? And this goes to 0. That's what I'm referencing here. Pn is equal to that. And that's what we used for the last like equation as well. So I don't see why it should be any different. Okay. I see P top, which should be the inside, is equal to the atmosphere plus 2 times surface tension divided by radius of curvature. I don't see anything wrong with this, I don't think. No, no, no. That's weird how they have it set up. Okay, so has it P atmosphere is equal to P top plus, but she wrote out the same like exact thing that I was talking about, whereas P in is equal to P out. P atmosphere is equal to P top plus rho GH. What did you get? Negative 70? Okay, well, the 70 is what I'm worried about, I think. The fact that it's negative or positive, I think that might just be an issue with her slides then. Maybe, I'm not sure. Because, like, I feel like, I mean, just P in, P out, right? So in would be inside the droplet, out would be outside. So in is clearly the top, out is clearly atmospheric, right? So if we say P in is equal to P out plus 2 gamma RC, right? Then if in is our, yeah, go ahead. That's so weird. Because that just goes against like what we did for this problem, for example, for B. Because I put like when I said P in, right? Right. So we did P in is equal to P out because this is pretty much the exact same thing. Where you have a fluid, right, and our P out was our atmosphere. Yeah, like part B is exactly the same as this part be right here pretty much. So I don't see why this would be any different. But I mean, as long as we have like the value itself, like I'm pretty sure it's 70. I don't see any problem with that. So, um, yeah, let's just stick with like 70.2. I think that's what we got. 70.2 pascals as our p-top for now. And I'll look into this a little bit more, and I'll let you guys know if I have any updates with this. But like, if you're getting negative 70, then 70 is the right answer, I'm assuming then. It just might be a difference in like how you arrange the equation in a sense. Because, I mean, if it worked for one problem the way we did it before, P in is equal to P out, where in was inside the droplet, out was the atmosphere outside, right? Then this in should be the P top and the out should be the atmosphere. And so I don't see why that would be any different. But yeah. Unless then like, well, no, that wouldn't make a difference either. Never mind. But yeah, I think it should be a positive 70.2. But gauge pressure can also technically be negative as well. Like if you're below atmospheric, then your gauge pressure could very well be negative. I'm also thinking like, well, hold up. So this might be, yeah, I'm thinking it might be negative 70. But once again, just the arrangement is weird to me. Because like we're assuming, right, based on the slides that you sent me, like we're assuming then that the or at least how we were thinking about it, is like the pressure on the inside of the droplet is going to be less than the atmospheric. Isn't that what she was saying? Because if that's the case, then if it's less than, yeah, if that's the case, then it would make sense that the gauge pressure would be negative. Because your gauge pressure is the absolute pressure. Yeah. Hmm. Well, from like a very strictly like scientific or what makes sense standpoint, it should be a negative gauge pressure. But from this equation, why it's not working out boggles me. Because mhm. I'm just confused as to why this like arrangement doesn't work. Like why do you have to have it as P atmosphere is equal to P top then? That's my only gripe. Maybe I'm just missing something. Yeah, one sec. Let me see because I might just be, yeah, that might be something that I'm missing. Um, but one sec here. Let me just look at what we have here. Mm-hmm. But I mean, it says it gives the pressure difference across the curved interface. It doesn't really differ between, or say that it differs between inside and outside, like that if it was curved inwards or outwards, convex or concave. But I'm wondering, like, if here, somewhere down here, will they have, yeah. So let me see here. They have hydrostatic pressure difference is maintained by the place pressure. Okay. Weird. Huh. Well then, I will just go with that then. So I'm not sure exactly why, like, this might be a little different. So maybe I'll just look in, maybe this, like that specific situation is a little bit different. But once again, like, oh, I see, maybe it's because like the radius of curvature here then is like pointed inwards, and then here would be pointed down. Ah, okay, that might be it. But yeah, I'll look into this a little bit more. Interesting. Okay, yeah, we didn't have like this distinction here when we did it, so yeah. I mean, honestly, same answer is just this. I guess maybe for this type of situation, we'll give you um, the proper way to do it, but um, in that case, right? If this is our p top, when we subtract over the 2 gamma divided by RC, and his atmospheric is 0 for the gauge pressure, we should add a little extra negative sign here, and that gives us a gauge pressure of negative 70.2 pascals, which makes sense once again because the pressure should be lower than the atmospheric pressure. I'm just wondering, like, then what's the difference between this? Like, did I just make the right guess essentially that it's curved this way instead of the other way? I'm wondering. It's like I don't see any other reasoning for that. But yeah, I'll just take a look at it later and figure it out if I can. But for now, I think this should be the proper setup. This is just based on your professor slides, so we'll just stick with that. Play it safe. But otherwise, the last part, C here, how high does the oil rise in the capillary tube? Use the hydrostatic pressure equation to relate the pressure at the top to that at the bottom, which is also at P atmosphere, right? So we were just looking at that in the slides, right, where they had rho GH is equal to 2 times the, wow, that's horrible, 2 times the surface tension divided by a radius of curvature, right? So if we have a radius of curvature from earlier, which is that 0.00114 meters, right? And now we're just trying to figure out the height, and we have the density, and we have gravity, and we have our surface tension. Then we can simply just solve for the height, right? So we can divide over the density and the gravity, so we can get 2 times the 0.04 newtons per meter, and then divide over the density, which was what, 700 kilograms per meter cubed, times 10 meters per second squared, and then times the radius of curvature, which is 0.00114 meters, right? And then that should give us the height, right? Let me calculate this out. So height, 2 times 0.04 divided by this, 700 times 10, 0.00114. Okay, I got like 0.01 meters, which is 10 millimeters basically. Yeah. Yep, sound good for part C as well. I think that's the gist there. But yeah, like I said, I'll look into this part B a little bit more just to make sure that this 70 thing is right, because I'm not too sure about the whole atmospheric is equal to top thing. Like maybe I'm just missing that. Maybe that's something they added from our lecture, because I don't have that on any of my slides, so I don't know exactly what the difference is there, but I can also ask one of the professors to clear it up. Okay, cool. But otherwise, I think that pretty much wraps up all of the problems there for this written homework. Like I said, I'm gonna have a review session on Tuesday, hopefully, to kind of just go over all of this stuff one more time from the lecture slides, and then afterwards it's just gonna be review sessions, the designated ones that we have. But yeah, and then yeah, one sec, I can go back to the last problem. There we go. Sorry about that. We can say that again. You were cutting out there. Sorry. No, I don't think so, because this right here will just be equal to the density times the gravity, and then this height is unknown, so we can't like have a specific value for this because we're looking for h. So we use the 2 times the surface tension divided by the radius of curvature that we got from part A, and then we divide by the density times the gravity, right? Because this p top here is going to be different than this rho gh here. Oh, I see what you mean. I see what you mean. Yeah, yeah, yeah. If you're talking about just like this part, yeah, you can just take this like 70.2 basically, and then divide over the density and the gravity. Yeah, you can do that as well. Yep, yep, yep. But we do have like 10 minutes left. I know, Carlos, you wanted to do some online problems. I don't know if we'll be able to get through a lot, but I also have to like just preface this and say like I do have some work that I need to get to be honest. Like I don't want to like just not be upfront with you. But let me see here. So let me pull up the oops. I'll go back to the online homework stuff. I don't know, is there one that you kind of had in mind? Because I know this stuff is like really intense, so I might not be able to like, because I don't want to start something and then like have not be able to like just finish it properly. So I'll tell you what. As usual, like feel free to send me a message, and I'll be more than happy to help you out with any of those online homework problems. No worries at all. But I just don't want. I just want to like start one midway through or something like that, and then end the session later on, just because I do have some work that I need to get to. Just want to make that clear. So I apologize if I'm not able to go through that with you right now. But yeah, no problem. And I'll end that recording on this note. So hope you guys enjoy the rest of your night, and yeah, good luck with the rest of your studies.